Well, welcome everyone. This is the SIGGRAPH 2020 course, a Whirlwind Introduction to Computer Graphics. Yeah, this is kind of cooler looking lettering anyway. My name is Mike Bailey, and I'll be your course instructor today. You have a web address. Let me move my little picture to the side. You have a web address there at the bottom, and these notes are available there along with a whole lot of auxiliary files that you can use in your own computer graphics experiment. So be sure to visit the website when you have a chance. All right, so why are we here? What is this course all about? Well, the course is to provide a background for the amazing things that you'll hear and see in the other SIGGRAPH 2020 venues, and to create a common vocabulary. That is, we can appreciate these other venues a whole lot more if we understand the words that they're saying. And again, that's part of what we're going to do here. All right, my name is Mike Bailey. I'm a professor in computer science at Oregon State University. I've been in computer graphics for over 30 years. Oh my God. And I've had over 8,000 students in my computer graphics courses at Oregon State. So yeah, this is cool. I just cannot get enough of this stuff. And really, that's what it comes down to, is computer graphics, cannot get enough of it. There's my email address. You're welcome to email me. I would love to hear from you. All right, so what are we going to do? The course is divided up into 5 major sections. There's a section right up front about how the computer graphics pieces fit together. Then we're going to talk about modeling and rendering and animation, and then included, and it's on the website, it's not in these notes, but it's on the website, is a finding more information document. And it's got some of my favorite book references, conference references, magazine, journal references. So be sure to check that out. That's kind of important. Okay, but the computer graphics process. What are all the pieces that go into making a computer graphics image? And we can really kind of break it down like this. There are a whole bunch of things, 3D motion, geometry, surfaces, texture, lighting, and so on. And all of it ends up funneling into the computer graphics process that ultimately comes up with an image. Okay, and so they can loosely be grouped into 3 categories: modeling, rendering, and animation. And these aren't exclusive categories. They can be, there's overlap in them. Okay, but let's talk about the modeling part of this. Modeling involves turning your ideas in your head into some 3D geometry. And you can provide surface information, you can provide texture information, but basically you want to present the graphics process with a full 3D representation of the idea that you've got in your head. Well, how do we do that? Before you model anything in 3D geometry, you really need to ask yourself some questions. What is the purpose of what you're doing? Do you want to just simply look at it? Do you want to interact with its shape? That is, do you want to sculpt it and pull it and so on? Or do you want to just put it in your scene and kind of forget about it? Does it interact with the environment? Are you going to ask it to fall down a flight of stairs and bump and roll? Do you care about things like its surface area and its volume? That is, are you looking to get some mechanical properties out of this? Will you want it to be 3D printed? And we'll talk about that a little bit, because there's some special things you need to do if your model's going to be 3D printed. Okay, and what's cool is if you're interested in experimenting with some free 3D modeling programs, well, here you go. Blender, SketchUp, Tinkercad, and we use these here at the university in some of our outreach programs, and so we've developed some notes for them to help people get started. So yeah, help yourself. But this is a lot of fun, and rather than just simply looking at these notes and go, whoa, that looks interesting, that doesn't affect me. No, no, no. go out, try some of these things. And in fact, some of these programs were used to generate some of the images for these notes. All right, so probably the most common way of representing 3D geometry is called a mesh. And models defined this way consist of thousands of vertices and thousands of faces. The faces are typically triangles, but I suppose they don't have to be. And it works like this. Let's say that this is the object we are trying to model, like, oh, duh, a cube. Okay, but it fits on the slide. You know, okay, great. We can do the Stanford bunny, but let's do a cube because it fits on the slide. Here's how you model that. We have 8 vertices because it's a cube. We have 8 colors because each vertex has its own color. And if we want to not list all the vertices over and over to make each face, we could just list them as indices, like vertex 0, 2, 3, and 1 become one quadrilateral, and so on. Now, typically we do this in triangles, and so if we did this in triangles, we would break up each face into 2 triangles, and the indices would be twice as many, but there'd only be 3 of them per row. The reason we like triangles is they're guaranteed to be planar. A quadrilateral doesn't necessarily have to be planar, and in computer graphics, we really like things to fit in a plane, and so yeah, we like triangles. 3D printing requires a triangular mesh. In fact, when 3D printing started becoming popular, triangle meshes became a big thing again. They had become a big thing, and then they weren't a big thing, but now they are because of 3D printing. So again, we will talk about this a little more later. But just to kind of give you an idea of what you could do with a 3D printer and triangle meshes, I took the SIGGRAPH logo and scanned it in and wrote a little program that looks at colors and turns that into a 3D mesh, and ran that into a 3D printer, and made a cookie cutter out of it. And yeah, delicious SIGGRAPH cookies. Why just go out and buy a bag of sugar cookies when you can make your own SIGGRAPH cookies? That's what I really want to know. All right, here are other ways of modeling. Sometimes the triangle mesh becomes a lot of pain. That is, there's a lot of detail in there, and we tend to look for ways of thinking at a higher level where we don't have to supply as much detail early on. And one of these is called, it's called several things: Boolean operators, constructive solid geometry, but it basically goes back to the Venn diagrams that you learned in high school. Oh my gosh, we're back in high school. Well, you remember how this worked? If we had 2 overlapping shapes, and really we were talking sets, but in high school, but let's talk about shapes. If we have 2 overlapping shapes and we do the union, we get the parts of the shapes that are in both. If we talk about the intersection, well, then we talk about the shapes that overlap. And if we talk about the difference, and I don't remember doing difference in set stuff in high school, but that turns out that's really useful here for modeling. Basically, one shape takes a bite out of the other. So if we extend this, what we learned in high school, to 3D, we get something like this. Here are 2 overlapping solids. The union looks like this, and it kind of looks like the same shape as we had a moment ago, but it's not. It's one object. That is, here, the overlapping solids, there's a certain amount of volume in here that is in both solids. That's not the case here. There is one outer shell, and only one outer shell. And this is wonderful for 3D printing, as 3D printers really hate in the screw up sense. They really hate when you have volumes in common. So union looks like this, intersection looks like this, difference looks like this, and you can do stuff with that. Other ways of creating 3D shapes or creating shapes at a higher level is called curve sculpting. Curve sculpting is, well, it's a lot like, well, imagine I had a piece of metal in my hand. I could twist the ends of it and it would make a certain shape. And depending on how I twisted my hands, it would make a different shape. And all the points along the curve would be known by the way I twisted my hands. Well, we can do sort of the same thing in computer graphics. This is a formulation called a Bezier curve, and it turns out there are probably dozens of mathematical ways of defining curves. This just happens to be one I like. But in that, we have 4 points. And as we move those 4 points around, very touchy screen pen. As we move those 4 points around, if we run through this equation, we vary t from 0 to 1 in some increment. Now, if we want 20 points along the curve, then we're going to make t go 0, 0.05, 0.1, okay? 0 to 1 in some increment, and the finer the increments you use, the cooler the curve is going to look, the smoother the curve's going to look. Okay, but the neat thing is I can pick up these points and move them. And if I pick up a point and move it, and then redo this equation, the curve changes shape. And this is really the essence of what you want in geometric modeling. A small amount of information in and a large amount of information out. Okay, the constructive solid geometry, the Venn diagrams, were really a good example of that as well. I had, say, 2 solids coming in, and going out, I could have turned that into a triangle mesh. Okay, small amount of information in, big amount of information out. That's one of the holy grails of doing geometric modeling. Here's an example, and there's a video on it. When you see these video, gotta find a place to put my face video that is not always in the way. When you see one of these little icons with a movie camera, go to the website and you'll find that MP4 file there and go look at it. Okay, because we're in the SIGGRAPH 2020 format, we've been asked to cut down the time for our courses. I'm not going to show the videos live, but please go do it, because this means a whole lot more when you can see things interactively. But this is making a shape, and so here we have the 4 points of a Bezier curve, and if I were to grab this one and pull it down here, I would end up with kind of a snarky looking eyebrow, and there's a lot to be said for good snark. But do take a look at the video. So anytime you see an MP4 file name with a movie camera icon, go look at the web page. And if you can do this with a curve, you can do it with a surface. And the surfaces, when you do it with a surface, those are referred to as patches. And just like there are dozens of formulations for the math for the curves, there are dozens of formulations for the math for the patches. And so that makes sense, but it's the same thing. And so for instance, here's a Bezier surface, and instead of having 4 points along the curve, it's got 16 points here. It's got 4, 4, 2, 2, so it's got 12 points on the outer edges and then 4 points in the middle, but it's the same idea. As you pick up one of the points and you move it, the surface comes along for the ride. You can see it a little better here without the wireframe lines. And this lets you sculpt. And The output of this is a gob of little triangles in here. That's what you need for a graphics display, is the triangles. And so this is, again, a very good example of a small amount of information in 16 points and a huge amount of information out, and that's what you want. The other neat thing personally I like about the surfaces is you can do analytic things with them as well, as you've got this mathematical representation of the surface, so you can start to do contour line equations, and yeah, there we go. And it's really kind of fun. If you move this point up and down, the contour lines start changing. Or in this case, it's showing curvature. This is Gaussian curvature, and it's showing principal directions here with the arrows, and it's showing absolute value of curvature with the colors. And again, as you sculpt one of the points, any of the points, all these things change. And it's quite instructive. And if you've got some goal about what it is you're trying to do, like I'm trying to maximize curvature at a particular point. Okay, I just keep moving points around until that happens. This is one of my favorites too. This is called a lattice, or sometimes called a cage. But the idea is, let's say we've got this Stanford bunny, and for some bizarre reason known only to me, I want to take this ear and I want to stretch it out. Well, if you remember back to that original triangle mesh image, there's a lot of triangles in there. And so to scoop up each of the vertices one at a time and pull it out is just horrific. And we're not going to do it. And if we did, it would look awful anyway. So here's the trick, is modeling systems will allow you to put a cube, kind of a cube of cubes, and this is what they call a lattice or a cage, and associate it with that ear. And so we've surrounded that ear with this cube of cubes, and now we can sculpt by pulling on the vertices of that cube. And when we do that, the vertices inside the cube of cubes get stretched out as well. And again, small amount of information you're providing, but a big amount of information is getting changed. And there's a nice video on that too, if you look at lattice.mp4. Oh, and there's all kinds of other things you can do, special effects. I'm very high on using Blender for a lot of these examples. Blender has this quick automated explosion feature. You know, if you can't explode a monkey, what's the point? If you can't set a monkey on fire, you know, what's the point? But again, modeling is a big deal. But if you're going to do something with it, like explode it or provide smoke, there's some extra information you need to have. And again, this all goes back to the idea of, before you model, you ask yourself the question, why am I doing this? And if we're not going to do these extra things, then we just really need to be concerned with appearance. All right. Objects must be a legal solid if you're going to do 3D printing. I mentioned we would do this. We'd come back to 3D printing. Objects must be a legal solid. There must be a definite inside and a definite outside. Here we've got a definite inside and outside sphere, except for this missing face. And so there really is no definite inside and outside, because I can pass between them. And am I on the inside or the outside? Well, I didn't pass through anything, so who knows? 3D printers get enormously confused about that, and in general screw up. So you got to be careful about that. Also, objects cannot pass through other objects. And in that first picture, when we looked at the Venn diagram, the 3D Venn diagram, where the cylinder was passing through the cube, well, they were overlapping. Okay, overlapping in 3D, cylinder passing through a cube, bad, don't do this. But if you do that Boolean union, that constructive solid geometry Venn diagram union, now there is only an outer shell. like that. There's nothing in the middle. There's nothing in the middle that overlaps. And that's what a 3D printer wants. Just for fun, I did this. I did both of these and sent them to a 3D printer. And this is what it did when I had done it correctly. And that's what it was supposed to do. A little nib of a cylinder sticking out. Here's what it did when I messed it up, when I deliberately made them overlap. And while that's wrong, it's not horribly wrong. That is, it didn't melt the machine or anything like that, but clearly this isn't what you want. All right, so that's modeling. And in that overlapping set of diagrams at the beginning, we talked about modeling, rendering, animation. So now you've got your geometry. Okay, now we want to draw pictures of it. How do we do that? Here's where it all comes together. When we did modeling, we provided surface information. Now we're going to use it. We probably provided texture information. Now we need to use it. So this is all the rendering step. Again, like modeling, you start by asking yourself, why am I doing this? You know, how realistic do I want it to be? Is this meant to be like a cartoon type 3D image? Is it meant to be a photorealistic 3D image? Am I doing Toy Story or am I doing The Lion King? You need to talk about that ahead of time so that you do what you need to do, but no more. Rendering is a very time-consuming process. And so if you are providing more, say, more realism than you need to, it's going to take a lot longer than you want it to. Okay, you want to ask how much compute time am I willing to tolerate for this? Do I need to take in lighting? That is, do I need to set it up like a sound stage where I have a bunch of lights all pointing at the object? Do I need to do global or local illumination? We'll come back to what that means in a little bit. Do I need to create shadows? Shadows is an extra part of the rendering computation. Do I need reflections and refractions? Will I have glassy things in my scene? Will I have mirrored things in my scene? Again, ask yourself these questions so that you understand why you're doing rendering, and then that helps you decide how to go about doing the rendering. And of course, everything you see rendered as SIGGRAPH, people have had to go through this process. Again, if you wanted to experiment on your own, I'm very high on Blender for generating examples, like for these notes and for things I do in class. And so there's a way to get started if you go to that website. All right, what about lighting? Well, lighting helps you figure out where the three-dimensionality of the surfaces are. So here, I can tell what these look like, oh, this surface is lighter than that one. There must be an obvious edge there. But if I don't take the lighting into account, well, there's no obvious edge there. You know, the edge should be right about there, but it's not. And so we can't tell. So, you know, lighting is typically a pretty important part of any sort of scene rendering that you do. Here's the difference between global illumination and local. Local illumination means light hits an object, it lights up the object. It lights up this object. It lights up this object, and that's the end of it. Global illumination means the light from this object being lit up actually is capable of bleeding out into this object and bleeding over into this object and so on. This is global illumination where the objects in the scene all impact each other. Local illumination means they only impact themselves. Why do we care? Because global is a lot more computation than local. And so if you don't care that the objects have some appearance interaction with each other, then stick with local. It'll be a whole lot faster. But you know, global is a whole lot cooler. Let's just face it. All right, the dirt simple way of doing lighting in computer graphics. I mean, so dirt simple that you probably don't do this except when you're teaching computer graphics to people, is called ambient, diffuse, and specular. Okay, ambient, diffuse, and specular, it works like this. First of all, here's the point we're eliminating. So there's kind of an underlying triangle or vertex sitting there. It has a surface normal. This is a vector coming off the surface that's perpendicular to the surface. Okay, and for things like spheres and cones and cylinders, it's pretty easy to find that. When you're modeling in a mesh, well, you have to be a little more creative, but there are ways. All right, we have a light. We're allowed to have multiple lights. Let's just say we have one. And so there's a light vector, an L vector from the point to the light. We have a vector from the point to the eye. This weird looking thing right here is your eye. And there's an angle here. Okay, so angle of incidence, and that's what this is. This is the angle of incidence equals the angle of reflection. So there's another vector right here, and I'm going to call that the perfect reflector. All right, so this is the situation that we're dealing with. ADS, ambient, diffuse, specular. Ambient is just a constant. It's light bouncing everywhere. Okay, diffuse, it accounts for the angle between the incoming light and that normal vector. Okay, and this is real. This is a law of physics. And so, well, gosh, we use it. And so it's the light intensity. The intensity on the surface is the light intensity times the cosine of that angle theta. The specular, and that's kind of the little reflective bright spot part of it, that is, we use this in the ambient diffuse specular model. We do this not because this is physically correct, but because it gives decent results. And again, this is why this isn't necessarily the model you want to use, but it certainly is a good place to start. The S power here is to raise the cosine to a power, and that makes the bright spot, the reflective bright spot, smaller. And the reason is, if I draw a graph of cosine to the 1 power looks like this, cosine to the 2 power looks like that, cosine to the 5 power looks like this. That is, you get a lot of fall off. The more you raise it to a power, the more fall off you get. And so you get a narrower bright spot, and that's kind of a visual cue to us humans that we have a smoother surface. So let's talk about that again. Diffuse is the angle between the surface normal and the direction to the light. And you know this from your own experience with flashlights. If you hold the flashlight perpendicular to the surface, that means that this angle is 0, and you get the brightest diffuse you can. If you angle the flashlight, this gets dimmer. But it's not that you're losing light somewhere. What it really means is, as you angle the flashlight, the bright area spreads out. And so if you think of the diffuse as sort of being light energy per surface area, you now have more surface area here when you angle the flashlight, and you're going to get less intensity. And again, specular, we use that cosine raised to the S because it gives decent results. Really the way this works is there's no such thing as a smooth surface anywhere. Every surface is rough. You may have to get down to the molecular level to see it, but we don't want to model at the molecular level. And so will do this. And so here's how it all comes together. And if you go to this MP4 video, you can sort of see the different components brought in and taken out. So ambient is a constant. Diffuse is, well, it's this variation in intensity around a curved surface. And then specular are the bright spots. put them all together, what have you got? You've got something like this. This is decent results. It's not super results, but it is decent. And in computer graphics, this has been used for a lot of years. Now, if we really want to do this better, we want to go back to something called the lighting equation. And here is the lighting equation. And you think, oh my gosh, will this be on the final? No, it will not. However, what will be on the final is this. And this is really what the lighting equation is saying. And the lighting equation is an energy balance. What it's saying is, if I'm at a point P, there is light coming in from everywhere. If I put a half sphere on top of me, there is light coming in everywhere from that half sphere. You know, maybe it's just the way I drew the diagram. To me, it looks like you're kind of standing in the bottom of a snow globe, but there is light coming at you from everywhere within the snow globe, and that includes all the objects that are in there with you. Okay, now the light, all that arrives at the point P, and what happens is it gets re-emitted from the point P, and we follow that. Now, if we're just rendering this, well, we only care about the direction to the eye, but if we're not just rendering this, then we care about where this light goes and how it bounces off of other objects. Okay, and so this is truly a global illumination method because you have light coming in from everywhere and every other object and bouncing back out to everywhere and every other object. Okay, yeah, this is the plain language. So do not memorize the equation, memorize the idea. Light is in balance. And this is really one of the reasons that the world in computer graphics has largely gone to things more based on this as opposed to ambient, diffuse, and specular, because here is the important thing. It's a light balance. That is, whatever light comes into the scene from lamps, from open windows, whatever, it never leaves the scene. It just keeps being balanced by the things in the scene. So something takes it in, it puts it out. Whereas ambient, diffuse, and specular, depending on how you crank up each one of those, you can end up with more light energy in the scene than you put in. And so, yeah, it doesn't, ambient, diffuse, specular does an okay job, but you know, we get concerned about the light balance, that we're actually following the laws of physics about energy can't be created. It just has to stay there. Okay, here's a great example of this. And you can see there's a lot of bleeding going on. The only light source in this scene is right here. And light from there is hitting the wall, but then the wall is reflecting out, and you can see some green here. You can see a lot of green here on the torus. Same thing with the red, you know, and actually you can see the red bleeding into the back wall and green bleeding into the back wall and red bleeding here and red bleeding there and so on. This is a great example of that energy balance. Is light energy is not created or destroyed, is just redistributed according to the rendering equation. Okay, when people start doing this, they come up with something called a BRDF. And BRDF stands for bidirectional reflectance distribution function. Go ahead, try and say that 10 times fast. And what it means is for any material, and people actually measure this. People shine lights on different material. They've got a whole bunch of sensors, and they look at this BRDF. And what they are asking is, for this material, for this angle of light impact, what is the distribution of the bounces coming off the material? And again, there's all kinds of papers about this. There's information about this, but if you want to do physically realistic global illumination, this is one of the things you want to know. Some materials are very smooth, and so they sort of focus the outgoing light. Some materials are very rough. You do a rendering of a rusty surface. Well, that scatters light all over. And so these are the kinds of things that people measure and record. And so imagine I've got a scene where I've got a light over here, and I could trace from the light. It's actually easier if you trace backwards from the eye, because really you're concerned with what can the eye see. And so if light from the light source bounces way the heck off the side of the screen, you don't care. What you care is what the eye can see. So if the eye is right there, let's trace backwards. And so if we trace backwards, this blue surface has a certain BRDF. We're going to say it looks about like this. And now we trace each one of those. And so if we trace, let's say this one, it hits the red surface, and the red surface has a BRDF. And we trace each one of those. And some of those hit the green surface. And then we trace some of those. And some of those then hit the light source. Okay, but now by tracing the BRDFs and the different surface properties, we now have a color. Yeah, that's probably a mix of the colors of the different objects that the eye can see. Now you can see the big problem right away, right? Right away is if I hit here and I put out a bunch of rays coming back off the blue surface, and then each one of those rays that hits the red surface, that itself spawns off a whole bunch more. And then each one of those that hits the green surface spawns off a whole bunch more. You've got like an N to the M problem. Is that by the time you're looking to see what hits the light source, you've got gazillions of rays. And so these kinds of techniques end up using some sort of Monte Carlo simulation. Monte Carlo, where you take sort of a probabilistic distribution of rays that come off the BRDF. Okay, and clearly the more you use, the better your rendering fidelity will be. But of course, you don't want to go too crazy, because then you won't get a rendering in your lifetime. So there's some interesting work that's gone on here, and some interesting work in accelerating that using the GPU. But a lot of the really great looking images you'll see at SIGGRAPH are created this way, with these BRDFs and with Monte Carlo simulation to keep the number of rays manageable. Oops. Here's an example. I did this with Blender, but here is the only light source in the whole scene. This is sort of like the little box with the red and the green. Here is a reflective sphere. So this is a mirror. Here's a refractive sphere. So this is like a marble. You notice we're getting soft shadows, we're not getting hard shadows. Well, that's because we've got this Monte Carlo set of rays going out, and some of them hit in the shadow and some hit outside. And when you collect them all together, you have soft shadows. We've got caustics going on here. I got impatient and stopped the render before this ended up looking really good, but same sort of thing. We have light coming through the refractive sphere, and it's bouncing through and creating these caustics. Caustics are like the light pattern you see on the bottom of a swimming pool. So this is an example of that kind of tracing. This is done using the cycles renderer in the Blender package. And you can have a whole lot of fun doing this sort of thing. You can even see it in the little title slides here. You know, Whirlwind Introduction to Computer Graphics, and there's green from the background bleeding on top of the characters. This was rendered with the Blender renderer as well. Yeah, one of our grad students here did this. This is, you know, pretty cool. Again, it's the path tracing, which is sort of an extension of ray tracing, but it's got the soft shadows, it's got reflections, it's got refractions. It is just a beautiful looking image. And there are lots of effects. And you'll see these when you watch the videos from SIGGRAPH, or when you watch a computer graphics movie, be sure to look for these. Like things like hair. Hair is what's known as an anisotropic material, meaning it has, well, it has different properties. You notice when you see the top of someone's head, you get that sort of ring, that halo of light. Well, why is it not a nice circle of light, a bright spot like we see in a lot of other renderings? Well, it's because the hair has different properties depending on the direction. For instance, if you are going down the head, you have a very slow curvature. If you're going crossways through the hair, you have a very tight curvature. And so the fact that you've got two different curvatures on the same object creates this not equal effect, anisotropic, not equal. Fur is also pretty tricky. Feathers are pretty tricky. They all have really interesting optical properties. So look at these. If you see these in a movie or computer graphics video, applaud for it, you know, because somebody has gone to a lot of effort to make that happen. And there's a lot of other things too. There is something called subsurface scattering, which comes about in rendering. And subsurface scattering kind of works like this. If I've got say an object here, and here comes the light ray, well, sometimes it bounces back out, and that's really what we've talked about just now. But for some objects, that light ray will go inside and will bounce around and come out somewhere else. Then that's called subsurface scattering. And some of the materials that do this are materials like skin, wax, milk, paraffin, and so on. And if you just simply turn it on when you're rendering, you can see the difference. So here it is without subsurface scattering. Here's what it is with subsurface scattering. And again, you can kind of look at this one and say, oh yeah, I can envision that being sort of wax, like a wax candle. Sure, we'll put a little wick up here in it. And now it's a monkey candle. Okay, so there really is almost no end to interesting phenomena that you can put into a rendering. So that's the rendering section. We've talked about modeling, making your geometry. We've talked about rendering, turning your geometry into a picture in some way that gives you the effect you want to have. Now we're going to talk about animation. See, look, green bleeding in the letters. All right, so how do you get things to animate? And there's a bunch of ways of doing that too, like you'd expect. Okay, 3D movement definition, but there's a lot of ways of doing the 3D movement definition. I think you're going to like this. But again, what's the first thing you do when you start doing this? You ask yourself, why am I doing this? What is it I'm trying to do? Do I want this to follow the real laws of physics? Do I care how much the object weighs? It will be sluggish if it's heavy. It'll be fast if it's light. You know, do I care about that, or do I want it to follow a certain path? Okay, are there certain key positions I want to make sure the object passes through? Do I want to simply record the motion of a real person or an animal and then play those angles back into the computer graphics animation. So a lot of things come into play here, and decide what you're trying to do and why you're trying to do it. And that will help guide sort of how much computation or what techniques you need. And we're going to look at some of the techniques. And again, Blender is a wonderful way to experiment with that if you'd like to do some of your own experiments. All right, the first thing is called keyframing. Keyframing as an animation technique really goes back to like the dawn of hand-drawn animation. You know, we're talking Walt Disney in what, the 1930s. And it works like this, is you have certain key positions that the object needs to pass through. So let's say that the monkey needs to pass through there, where it is now, and here, and over there, and over there. Well, in the days of hand-drawn animation, those were known as the key positions. Okay, wasn't every frame, you know, there's a lot of frames in between, a lot of frames in there. Stop it. There's a lot of frames in between, but these are the key positions. And in the pecking order of hand-drawn animators, the tradition is the senior people, they got to decide the key positions. Those were the creative decisions. Where are the key positions where people want to be? And then they would pass it on down the pecking order. In the next layer, they would get to pick some of the in-between frames, not all of them, but you know, some in between. How does it look in between? And eventually it would get down to the very bottom of the pecking order, and people would get finally to assign the individual frames. Okay, and so the person who got to assign the key frames, well, that was called keyframing, and the people who did the frames in between the keys were known as in-betweeners. And the terminology has survived into computer graphics, and really the technique is sort of the same, where except you are the top of the pecking order and the computer is the in-betweener. So the idea is you specify certain key positions of your object, and the computer fills in the key frames. And it does that by generating curves. So here's a key frame. This is the Z coordinate for the monkey. And here's another key Z value, and here's another key Z value, and here's another key Z value. And the computer has fit a nice smooth looking curve in between them. And if you sample points along that curve, like gosh, remember back to modeling several minutes ago, where we talked about getting points along a Bezier curve, small amount of input, big amount of output, exactly the same thing. And in fact, you can even sculpt the curve. And so if I don't like the motion, I don't kind of like, is it coming in too quickly? Is it coming in too slowly? I can take this line, this orange line, and I can twist it interactively by grabbing these endpoints and control the slope right there. And so I could set it up that it comes in lower and then goes up like that, or I could set it up that it comes in here and goes like that. But the point is, you are doing the keyframing and the computer is doing the in-betweening. So if you go to this MP4 file, you can see that in action. And it's a simple thing, you know, the monkey jumps over the cube kind of squishes to get out of the way, but it works. And you can do things where you groups of vertices together. And this is really pretty cool. It's called skinning. It's sort of like, well, you've got this sort of skeleton, and those are called armatures. These little things here. Think of them as the bones in your body. And then out here is the outer skin, your muscles, and so on. But you can make these bones you can connect these to that, And as you move these bones, move the armature around, this moves. This was part of an animation I attempted to do. I'm still thinking about it, where I wanted to have a character called Mac. He would be one piece of a macaroni and cheese dinner. and he was going to do some stuff, and okay, so it looks better in one frame than it did in the animation. That's why you're not seeing the animation, but I'm still working on it. I'm still thinking about it. Other things, what if things are connected? There's something called forward kinematics, where things are connected. So if I have this green piece and there's a pin right here, and if I have this red piece and there's a pin right there, well, this is called forward kinematics. It's also sometimes called hierarchical transformations. But the point is, if I move object number 3, 1 and 2 stay right where they are. If I move object number 2, then 3 comes along with it. And if I move object number 1, 2 and 3 come along with it. And so mathematically, you build in that sort of parent-child relationship. And a lot of things work that way, like the bones in your body, your arm bone and your forearm, and then the bones in your hand. And so a lot of things can be done this way. And really, you've known this for years, right? Anybody with a set of Tinker toys, by the way, this is my set of Tinker toys, not my kids. They think it is, but it's not. But anybody who's played with Tinker toys knows how this works and is familiar with it. And there's a lot of things you can do by modeling it that way, because then you can say, oh, let's just move the green piece in multiple places, and we don't have to model. We don't have to animate the red and the blue pieces at all. The equation of this kind of connection makes them come along for the ride. Okay, that's forward kinematics. There's another part of this called inverse kinematics, and it's really abbreviated IK. And as best as I can tell, nobody in their right mind calls this inverse kinematics. That just flags you as a newbie. So if you want to talk about this, call it IK. Oh yeah, that looks like a good use of IK. Memorize that, practice using it in a sentence, and it'll be great. You'll look good. But the idea is exactly the opposite of forward kinematics. Forward kinematics says, if I know those angles, where are the pieces? Where are the objects? This one says, if I know where I want the objects to be, what angles do I need to apply to get them there? So for instance, if I wanted the tip of the blue piece to be right here, the star position, then I could work it backwards and compute the angles I need to apply to make that happen. That's known as inverse kinematics. And early in computer animation, when they had a character walking, they did it with forward kinematics. And oftentimes you would see the foot kind of going into the ground, or the step and the foot's above the ground still. Of course, now you do inverse kinematics and you say, I want the foot to be perfectly on the ground, and then it works it backwards to figure out what the angles need to be. So it's goal driven. The goal is where you want the pieces to be, and it figures out the parameters to put them there. And again, all children know this. You also know that there are certain positions you can't get to. Think of trying to scratch that part in your back that always itches that you can't reach. Yeah, there's no guarantee that all positions are reachable by inverse kinematics. And the algorithms to do this point that out. And of course, you can do all kinds of things with human motion or animal motion. That is, when you connect these pieces together, essentially you put a joint here, you put a joint here, 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 and so on. And so what you've done is you've taken a bunch of disjoint objects, but you've made them into a head, a torso, an abdomen, legs, arms, and so on. Another interesting thing in animation is to do particle systems. Particle systems are just very cool. And particle systems can model so many different things, can create animations of different things. Particle systems basically means take thousands, millions, billions of particles and control their motion. Either do it from physics or make them look like what comes off of a flame, or make them look like fireworks, or make them look like sand or blowing dust. There are just so many things you can do with particle systems. And once you're aware of them, you can't stop seeing them. They are just like everywhere in games and movies. So yeah, get used to the phrase. This is one that I was kind of playing around with some GPU programming, but it's like a million particles and it's drawing them at a rate of like 1 billion particles per second. You know, particles in a GPU really work out very well, but become familiar with the phrase particle systems because they are literally everywhere. You know, falling water, waterfalls, spraying water. Yeah. So the basic thing in a particle system, and it's really a simple set of steps, is you emit the particles, you display the particles, and then you have some way of updating the particles. What laws, what effect are you trying to update the particles with? Yeah, this is something one of my cool grad students did. He wanted to experiment with sort of flying water being shot from a hose or something like that. But even here where it does look like the water is kind of blobby, it's not. It's really particles that have been joined together. I guess I should warn you. Um, I sometimes give particle system assignments in some of my classes, and there is no end to the effects. And so students can't put them down. They can turn them in, but they keep working on them and they keep adding more and more and more. Particle systems grab you and don't let go. Be very careful about implementing a particle system because 10 years from now, you'll still be working on it. This is some particle systems in Blender. You can combine particle systems with physics. And so really the particles are coming off the cube, but they're bouncing off those teal looking planes on the side. They're kind of coming down through this crevice. I was trying to make like an hourglass effect where they come down and drop out the bottom. It sort of worked, sort of didn't. And then some of them end up in the box. And if they hit in the box, they end up bouncing around and then staying there. But some of them miss the box and they go off into space. And again, check out the MP4 file. But this is ridiculously easy to set up because they're particles. They all follow the same general law. You just apply a little bit of randomness at the start so they don't all do exactly the same thing. And there's physics. Physics is our friend. Even if you took a physics class and hated it, it's still our friend in animation. Remember Newton's law? Actually, it's not his first law, it's his second law. Who wrote that? It's a second law, force equals mass times acceleration. And what we really care about is acceleration equals force over mass. Okay, so if I know what forces are being applied, yeah, such as gravity, such as a spring, and I know the mass of the objects, well, then I can figure out what their accelerations are. And from that, I can get their velocities. And from that, I can get their positions. So here's something that I put together in Blender. It's got these blocks here. They are, and here's the MP4 file. The blocks are all vertical. They're just standing there like books on a shelf, except for this first one. And this first one is leaning just a little bit. So when you start the animation, gravity starts pulling on this, but then it hits this one, and so now it's tipping. which hits this one, and now it's tipping. And then eventually this one starts falling, and it hits the sphere, and it pushes the sphere off the table and out into space, never to be seen again. To set this up and make it do that, well, if I was doing keyframing, it would take a long time to do that. And it probably wouldn't look realistic because I would probably not be good enough at it to make it look like the acceleration due to gravity. But all you've got to do is set some masses, set some things in motion, and let the math and the physics take care of it. And so this is a big deal. The good news is you can do this. You know, the bad news is you have to supply all those physical properties: mass, center of mass, moment of inertia, coefficients of friction, coefficients of restitution. But so it's a trade-off. And again, this is why you start the animation process saying, what is it I'm trying to do? What is it I'm trying to accomplish? What effect do I want? Do I want it to look physically realistic, or am I just telling a story? I like this though. I kind of like doing the physics. And of course, what would any discussion of physics be without fluids? You see this all the time. The Disney movie Moana was just like stunningly amazing in its use of fluid simulation. Again, another video. Springs can do an amazing amount of things in animation. Even if you don't really have springs, they provide certain behaviors that we like. For instance, you know, if I take, let's say I pull down on the spring a certain distance, the distance you stretch a spring is equal to the force that is in the spring divided by the spring constant. The spring constant is like a stiffness. Okay, how stiff is the spring? Slinkies have a very low K. They are not very stiff. Okay, but if I apply a force divided by the spring constant, that's the distance that the spring will stretch. And this is known in mechanical engineering as Hooke's law. But what if I put a bunch of them together? So now I've got a spring and a spring and a spring, and some masses here and some masses here. Well, this is a way of approximating a lot of things, like say a string. And so if I take that idea and I make a string out of it, I can sit up here and shake that top node, and the spring does, or the string does what strings do. Or you can make it a little stiffer and make it a chain. And if you go look at this, that's MP4, chain.mp4, you'll see that. Okay, but again, if I was going to keyframe this, first of all, it would take forever. And second of all, I probably couldn't do it well enough to make it appear like it's obeying some laws of physics. And once I've got this set up as a bunch of springs, I can change the spring constant, the stiffness. I could change the damping, like how much energy does it lose. I could make gravity go in any direction I want, be any value I want. That is, there are, again, small amount of input in, big amount of input out. You know, the small amount of input is this position and the characteristics of the springs in between the yellow dots. And that's it. And then it behaves. Yeah, we can put barriers in the way and it just hangs over the barriers like it should. And whoops, we can go sideways. That is, okay, here's one of what we had before, but what if we put a bunch of them together and put springs going this way and springs going this way and springs going this way, and we can get cloth animation that way. Now, we also put a spring diagonally, and the reason is if you only do left, right, up, and down, you get a sort of the appearance of fishnet, sort of that sort of motion as if it was fishnet. If you want cloth, you make it a little stiffer by putting a artificial spring diagonally. And so now we can do the exact same thing we did with the string. And again, small amount of input in, big amount of input coming out. that is small amount of input. On this one, we're shaking right here, and large amount of output because all of these little nodes are behaving like cloth, including draping over things, including automatically forming pleats at the bottom of the curtain. So yeah, it's cool. And Blender, this is from Blender. Blender's got an automated cloth animator in it. Now, what if you're doing something like this? This is students rushing the football field. So imagine all these things coming at each other and they're trying to get somewhere. They all have a target they're trying to get to, but they're trying not to hit each other. How in the world would you animate that? Well, this is something called functional animation, and I think it's really cool. I like to refer to it sometimes as fake physics. And that sounds derogatory, but I don't mean it that way. I mean, we're going to accomplish something really, really cool by pretending there's physics that isn't really there. And here's how we're going to do it. So let's say that this is one person, and this is where they are right now, but this is where they're trying to get to. And we're going to put a spring. We want to motivate them to want to get to their target, and so we put a spring on them. Yeah, imagine we did that to you, and we hooked up the other end of the spring to the water fountain. Okay, you would naturally try and get to the water fountain. This is the mechanical engineering symbol for a damper. It's just something that takes energy out of the system. Otherwise, you would go to the water fountain and, like a bouncing slinky, you would overshoot and then you'd come back and then you'd overshoot and then you'd come back and you never would get to the water fountain. So that's to take some energy out of the system. But this now motivates this person to want to get to their target. Now, how do we handle, and again, this is fake physics, there's no spring in there really. How do we handle them avoiding each other? Well, we make up more fake physics. Let's make up an imaginary repulsive force. And each one of these particles repels each other according to some repulsion constant magic. Here's the distance between the bodies. Here's sort of a power to let us make it stronger or weaker. Like, are they repulsed by each other a lot or just a little? And so now we have a motivation to get to the target, but also a force motivation to not hit each other. And so if you do this, if you fire this off, this is the kind of thing you get. And you can see it in the video. The video is a lot more interesting than the diagram. But as, say, this one, it started up here. So as it tries to get to its target, it encountered something and it figured out how to go around it and then get to its target. And so looking at these traces, you can see a lot of that, where they were on the way to the target and then they had to move around to get around something. And this is a great way to do that. It's not physics in the sense where you had to provide exact masses and so on, but it's not keyframing either, where you had to come up with all those positions. And so this is really a lot of fun if you attempt to set goals and make up, totally invent physics that makes you want to go to the goal. And you can play with the stiffness of the spring, and that gives it different behaviors. You can play with the repulsive coefficient, and that gives it different behaviors, and so on. And finally, in animation, there's also motion capture. Except never, ever, ever call it motion capture. It's mocap. Okay, you always call it mocap, otherwise you're flagged as a newbie. And the idea is actors wear suits with special things on them and sensors in the room to look at those things and decide what the 3D coordinates are. And then they apply those 3D coordinates to the computer graphics. So here's an actor doing some skateboarding. Here is the computer graphics representation of that. This is really great. You know, sometimes in a game you see people kickboxing. Kickboxing would be so hard to keyframe. You just don't want to do that. And so this is the kind of thing where you just have somebody go through the motions, capture their emotions, and apply it to the computer graphics. So here is the summary. We had modeling, we had rendering, we had animation. Put it all together, what have you got? You have computer graphics. You have computer graphics in games, you have computer graphics in movies, you have computer graphics in art, you have computer graphics in architecture, mechanical design, medical graphics, but it really comes down to these same three pieces. All right, so here is my bottom line. SIGGRAPH moments will never come again. And I've said this for years when we were all going live to SIGGRAPHs, but it's true now too. Okay. Okay. So some of the things are being recorded. They could come again, but some things will not. Be aware as you attend virtual SIGGRAPH, be aware of what's going to be archived and what isn't. If there are live sessions that are not being recorded, pay a special attention to those because you can't relive them afterwards. If something's going to be recorded, you don't have to watch it live. You can come back and watch it on tape. So SIGGRAPH is this sort of multi-ring circus with so many things going on. You really have to be strategic, and be strategic with your own personal and career goals as well. That is, go to the things that really are going to make a difference to you. Okay, this one looks fun, and yeah, if I have nothing else to do, or if I can see other things later, I'll go to that. But what are your career goals? What are your personal goals? And SIGGRAPH is a great place to go indulge your personal and career goals. Make sure that you do that. Now, I mentioned there's a finding more information. There's a document on the website, and I put it there just so I can keep it updated as I learn new things or find new books. But go to there and you'll find it. It's got computer graphics books, it's got publications, it's got other conferences. And if you hear about other things, let me know. And so that is it. I thank you so much for being here. It is such a thrill to be able to be a part of the SIGGRAPH conference. I hope to get to meet you all in person sometime. Thanks.